Am I doing it too, sir?
Yeah.
Almost.
Yeah, just a new page though. Alright, so we're going to look at derivatives of log functions. Derivatives of log functions are fairly kind, I think. They're not as nasty as they probably look. Obviously, we're looking specifically at natural log, so it's got to be log base e. So make sure that we're dealing with natural only in this scenario. Just for this rule here. Now the formula sheet gives you, this is my least favourite rule in the formula sheet, they give you this. And that's not very helpful. It is only helpful when log of x comes along, ln x comes along, which isn't very frequent. I much prefer this. What's that law saying? What do you reckon, Liam? What do you think that law is saying on the... If I've got a function ln of some function, the derivative equals?
The derivative of that function over the original.
Correct. So in this case here, what's the derivative of x? 1, correct? So it's the derivative function divided by the original function. That's all the law is. So it's quite kind in that regard. We'll go through a couple of examples here. I've got ln 4x squared. So I simply say, what's the derivative of 4x squared? Am I done? What do I need to do? Yeah, simplify. So I can cancel this and this, correct? And that will leave me with 2. Am I done simplifying? Over x, very good. So my final answer would be 2 over x. Cool? Vice versa. Not vice versa, sorry. Another example. I'll let you guys have a crack at this one first. I want you to write down what you think the answer is for that. I'll give you 10 seconds. I'm going to ask people. Write down what you think the answer is to that. The original function is ln or log base e cos of x. What is my derivative function? Thank you, Amber. It is sine. Sine x over cos x. And the only trick here, we have to be remembering with our derivatives of cos functions and sine functions, one of them is negative. I forget all the time which one's negative. So which one? Sine going to cos or cos going to sine? Cos going to sine, we think about the way those graphs look. Remember our cos function starts high and goes low. And if we draw our tangent, it's going to start going negative, correct? So it's negative sine over cos x. Does anyone notice how we could write that? Negative tan x.
Yeah.
Cool? So really with deriving natural logs, it's not overly challenging. What's probably the hardest part of it is the simplifying at the end. Be aware though, Abby gave me a great example before of a question. She gave me an example of, she said, it's a really good one, I'll write it up here, fx equals ln x squared plus 2 squared, or something like that. There are 2 ways I could deal with this. Who could see how I could deal with this problem? There are 2 possible methods of dealing with this problem. Chain rules 1. Absolutely. We've got a function inside a function. Perfect application of the chain rule. Easier way. I can take this at the front, can't I? So what I'm really asking for and then we can just use those laws there. So the second method, I should have written it below the second method, is the plug law. Oh, probably not, but I call it the plug wheel because you plonk it out the front. Yep.
Where does the 2 go?
This too.
No, when you've got 2ln, does, like, once you've derived it, does it just stay in front of h of x?
Which one? For this one?
Like, if you were to put...
Oh, to derive that? Yeah, so for example, what's the derivative of 2x? Well, it's just 2 times the derivative of x, which is 1. So with our constants at the front, they just stay, and we multiply them after we've derived it. So I'll do it, I know what you're sort of saying. So you're saying f dash x would equal 2 times h dash x over hx, which would equal 2 times 2x divided by x squared plus 2.
Oh, okay, so we keep it there and we find
Yeah, and then at the end you bring it. Cool, great. It's just a coefficient or a constant at the front.
Yep.
Any troubles with that? So either method's fine. The whole point of this, and this is what the challenge of maths is, every day we're adding things to our tool belt. We're saying, well, we can apply the plug law, we can apply the chain rule. We've got all these tools. What makes a skilled mathematician is like a skilled tradesman. It's knowing when to apply the tool to the right job. So looking at this problem and saying, look, I can use a chain rule there, great. Looking at this and saying, I can apply the plug law, great. Sweet? So if you nail that, you're really starting to understand how this works. Happy with that? Good work.